Hello and welcome to the Pre-Calculus Podcast. I am your host and wait, you didn't edit it. Hold on 1 second. I gotta do everything myself. This is like a one-man show or something ridiculous. Season 10 episode what episode? 6, 4, 8, 7. Okay, 7. And we're good, right? There we go. Gotta do everything myself. And why are there these black bars now? What? Hold on. We'll be BRB. Welcome back. Apparently my producer says that we can't get rid of those black bars once we've started, so just deal with it, people. Okay. Episode 7 of Season 10. Look at that. We're wrapping up this super quick. Parametric Equations is what we're looking at on this Pre-Calculus podcast. Again, I am your host. So, parametric equations is basically an equation with 3 variables. So you have your 2 main variables in your equation, but now you've thrown in a parameter. Usually that parameter is time, okay? Usually that parameter is time and it's t. So if we have our calculators and you push the mode button at the top of your TI-84 or 83, you'll see, when you push mode, you'll see it says like normal, float, radians, degrees is how we change it. Right below radians and degrees, you will see 4 things. You'll see function, par, pole, and SEQ. We are looking at parametric, which is PAR, so the par one. That is going to be parametric. Now, if you go and push y equals, you'll see you have a completely different setup. It says x1 t is equal to y1 t is equal to. And so when we do these, we have 2 separate equations and we have a new variable. And what we're trying to do here is that we're trying to find what our x and y is. And so what we have is our x is changing over a course of time and our y is changing over a course of time. So if you go to your calculator and you type in these numbers, so you end up with, once you have parametric and you type in your numbers, you go 1/2 and then t, which is the same place where you would usually do your variable. So your variable is usually that x, it's that xt sigma n button right next to alpha. You push that button and it's going to pop up with a t because we're in parametric. And then the second equation, we go t squared minus 3. Now if you go to your window, okay, you see at this very end, this is your t-min, this is your t-min, and this is your t-max. Okay, and that's your t-max. So your t-min would be -3, your t-max would be 3. The step, you can have it as, I usually do it about 0.1. X-min, we can have it at, I don't know, -5 to 5. And our scale can stay 1, and our y, we can go -5 to 5 also, just because why not. And then if we push graph, we see we end up with a parabola. Now, I'm going to extend my y max up to 10. Now, if my y max is up to 10, I would see that I have a parabola that stops. It doesn't go all the way, it stops. And that is what happens with a parametric. Parametric functions are only looking at this equation within the t from -3 to 3. So if the t is larger than that, it'll expand it. If it's smaller, it's going to be less than that. Okay, so turning a parametric equation into a rectangular equation is fairly simple. All you have to do is you take this equation, okay, solve for t, and then plug it into the other one. Okay, so I've solved this equation I circled for t, which gets me 2x is equal to t, And then all I've done is I've taken this and I've plugged it into the t of that equation. Okay, so I've plugged into the t of that equation. And that gets me my y equals 12x minus 7. Now, as you notice, the parameters changed, or my domain has changed. And how I got my domain to change is because what I've done is I've taken -1, plugged it into t, and solved it. I get a -1/2. And then I've taken 6, plugged it into t, and I've solved for my x for both. So to find those, what I've done is I've plugged in my bounds of my t into the bounds of my x. And that's going to change my x values and give it a different bound. Okay, because we're looking for a different domain with these. Alright, so let's say I have this function and I want to turn it from the turn it into rectangular. So if I want to take this and I want to turn it into rectangular, what I want to do is I want to try to get the t's by itself. Okay, so the easiest way actually to do this is not to get the t's by itself, but to get the trig functions by themselves, so the cosine and the sine t's by themselves. And so when I do that, I subtract 1 for the x and subtract 2 for the y, and then I divide everything by 2. So now I have this equation up here. Okay, and now what I have is I can use this right here, which if you remember is called the Pythagorean identity for our trig functions. Sine squared plus cosine squared equals 1, which is always true. And so we have those, and then we just plug in, because we know what cosine and sine is, so we plug them in and square them, and we end up with our answer. And this ends up being a circle. So if we were to graph this originally, we would end up getting a circle. So anytime you have sine and cosine in for both functions, sine t and cosine t, you're going to be using the Pythagorean identity. Okay, Pythagorean identity of sine squared plus cosine squared equals 1. Same thing with any of the other trig identities that we have. You can still be using it. So this would be a circle with a radius of 2, and the center is at 1, 2. Okay, going from rectangular to parametric is fairly simple, but there's an infinite number of answers, because what you're going to do is, if you're just given a rectangular equation, y equals 6x squared minus 5x plus 9, what you're going to do is you have to make up your x equation. So you have to say x is equal to what? T. You can make it x equals t, very simple, and then your next equation is going to be y equals 6t squared minus 5t plus 9, because all you're doing is that you're replacing the x's with t's. Now, if I changed and said x is equal to 3t, instead of replacing all the x's with just t, I'm replacing all the x's with 3t. So 3t squared is 9, 9 times 6 is 54, and then 3 times 5 is 15, and that's why we get that minus 15t. Okay, so it depends on what you pick as your x equals function, x related to t, because that's going to change what the y is. Okay, they're still going to get you the same shape. They might be have to be in different bounds, but for the most part, we're just looking for going from rectangular to parametric. You make your function, make your x equals t is the easiest. You should probably use that one. Other times they might tell you what the function is, so rewrite this into parametric with x equals 4t plus 7. Okay, and then which you just plug in 4t plus 7 into all the x's into the equation. Okay, projectile motion. Now, with projectile motion, you basically have two formulas, and we're dealing with it, our objects on Earth. Okay, so we have our acceleration of gravity, which is 32 feet per second squared, or 9.8 meters per second squared. We're going to be dealing with it in feet, just to keep it all uniform. If you take physics, we usually deal with this stuff in meters, because it's the SI units and it's the better one. Go science. And so we have our x and our y. So our x value is our horizontal change. So it's how far you're traveling horizontally, and your y is how far you're traveling vertically. And so here's your equation. You have x equals the velocity that you originally started with, times the cosine of the angle in which you're shooting something, times how long it is, so t. So that t is outside of it, that the angle, Y is equal to h, which is the original height, so how high you are originally. So if you're shooting something off the ground, the h would be 0. If you're shooting something off of a 100-foot cliff, it'd be 100. V sine theta t minus 16 t squared. And this 16 ends up being, gravity is negative 32, but we always do half of it. So, and that leads us into like when we do some calculus and derivative stuff, we can get back and find the acceleration of different things. And so gravity is negative 32 feet per second, so we always cut it in half because it's always half gravity for these equations. So we do half gravity for them. Okay. All right, so that's our formulas for projectile motion anytime we're lobbing anything. Okay. So let's say we have this. Brendan hits a ball and it's 4 feet above the ground with an initial velocity of 120 feet per second. The ball leaves the bat at 30 degrees, at a 30 degree angle above the horizontal, and heads towards a 10-foot fence 350 feet away from home plate where he hit it. Taylor backs up to the wall, trying to retire Brendan. For those of you who know baseball, will Taylor catch the ball that Brendan hit, or will Brendan circle the bases? Will he hit a home run? For those of you that don't like baseball or don't know baseball. Okay, so with this one, what we need to do is we need to find out, how long it would be, how high the ball is up in the air at 350 feet. If it's over 10, then that means he has a home run. If it's under 10, that means that he's out. Okay, so if we look at this, to try to find what it is, what we'd want to probably do is find how long it takes for that ball to travel 350 feet horizontally. So we're going to go up to this equation at the top, and we're going to go 350 equals our initial velocity, 120 feet per second, okay, times the cosine of 30 times t. And we'd go through and we'd solve this. So make sure your calculator's in degrees, not radians. So we'd go 350 divided by 120, divide that by the cosine of 30, means that the ball was in the air, or that it would take the ball about 3.368 seconds. We'll underestimate it just to help, so 3.87 seconds. That's how long it takes for the ball to travel 350 feet. So now the next question is, how high up in the air is it? Okay, so now we're going to use the second equation because that tells us how high up and down. So that one's going to be y, let's change the color up. So it's going to be y is equal to the original height of it. He hit the ball 4 feet off the ground, okay, plus the initial velocity, 120, sine of 30, and then we plug in our t, which is 3.367 minus 16 times 3.367 squared. Okay, so now we go through and we solve this. So take a second, solve it, see how high the ball is up in the air for this. Okay, so hopefully we got an answer of about 25 feet, 24 and a half feet. Okay, I think mine came up with 24.63 feet. Okay, so if that is the height at 350 feet away, would he have a home run or would he be out? Answer would be that he had a home run. It's over 10 feet, so that means he's going over the wall. Okay, so here's the setup. Looks nicer. Everything can see. Okay, so we have our time of 3.367. So what was the height at that? 24.59. I was a couple 0.04 off, but it's because of rounding errors. But as you see, it was over enough that it's going to be. So that means that yes, he has a home run. Okay, yeah, unless Taylor can jump 25 feet. But obviously you can't do that. So home run. So that is parametric functions. That is dealing with a x and y equation with a parameter of time in it. Okay, so it's an x-y equation with a parameter of time in it, and that is our new, our last section in this one. All right.